In this demo, I'm going to be walking across a tightrope-like object that's elevated in the air. And the first time I walk across it, about 2 meters, I'm going to keep my hands closest to the center of my body so that my rotational inertia is really small. This way I'm more susceptible to tilt back and forth, and you should see that it's really hard for me to walk across. Here we go. As you can see in these next two clips, it doesn't matter if you're bigger or stronger or anything, the rules of physics still apply. So if your arms are closer, you are going to be more likely to fall over it, versus if your mass is distributed, it's going to be a little bit easier. So as you can see in that one, I was wobbling back and forth a lot. It was really hard for me to balance. So this time I'm going to be taking 2-meter sticks. I've shifted one out, so it's about 1.5 meters. And I'm going to put 2 weights at each end. And this is so that I am distributing mass further away from the center of my body. This way it creates a higher rotational inertia, and I will be less susceptible to tilting or wanting to move in a different way than straight up and down. So let's see how this works.
This demo will explain the conservation of angular momentum. A torque is created while in contact with some other object. In this case, the gymnast's torque is created by the rebound force of the trampoline pushing against her feet. Once she is in the air, she is no longer subject to external forces. So her total angular momentum will be conserved until she hits the ground again. She has generated this angular momentum off of the trampoline. Her center of gravity is now forward as she starts to flip. Once in the air, she can't change her angular momentum, but she can change her moment of inertia. She can change her angular velocity, or the rate of which she's spinning. If she wants to spin fast, she tucks her knees tight into her chest, giving her a small moment of inertia. If she wants to spin slow, she stretches out as tall as possible, giving herself a large moment of inertia, spinning slower. In order to get a balanced seesaw, the net torque must equal 0, which means the torque of each individual on the seesaw must cancel each other out. Torque is equal to the force times the distance, the force being the weight of the individual on one side, multiplied by the distance they are from the pivot point of the seesaw. If a lighter person, or mass of 1,000 grams, is put on one side of the seesaw and a 2,000 gram mass placed on the other end, the seesaw will tilt towards the heavier mass, holding the lighter mass in the air. The mass on the right is 2,000 grams, and the mass on the left is 1,000 grams. In order to get these masses to balance and have their torques cancel each other out, we must move the heavier mass closer to the pivot point. Right now, both masses are 2 feet from the pivot point. When the heavier mass is moved a half a foot closer to this, it still doesn't balance out. When we move it another foot closer, so it is only 1 foot from the pivot point, it balances because a mass twice as heavy must be half the distance closer to the pivot point than the other. Now these two masses are balanced and have a net torque equal to 0, so if they were people, they would be able to play on the seesaw. However, after this, when the heavier mass is moved half a foot from the pivot point, the seesaw becomes unbalanced again, and the lighter object is on the ground while the heavier object is suspended in the air. The person on the left is heavier than the person on the right, so he falls, suspending the other person in the air. If two individuals of different masses want to play together on a seesaw, they must find a way to balance each other out. By moving the heavier mass closer to the pivot point, they can become balanced. However, if the heavier person is brought too close to the pivot point, the lighter person will be on the ground while the heavier person is in the air.